Okay, so here are the last of the examples for finding limits at infinity. That shortcuts, you learned it last year, and so I just want to review it with you and then maybe give you a couple that you didn't see last year. So first, the limit is x approaches infinity of 3x minus 2 over 4x plus 1. We are looking at the degree of the numerator and the degree of the denominator, which is the same. The highest power is x to the first for both of them. So this answer is just the coefficients of that highest term. And it doesn't matter if you're doing x approaches infinity or x approaches negative infinity, you're going to get exactly the same thing. And if you think through that just a little bit, and then the first one, example one, you have a big positive number, plugging in your infinity here and here, big positive number divided by big positive number. In an example two, if you plug in big negative numbers, you have a negative divided by negative, which is also positive. So if the degree is the same, then it's the coefficient of that term. You do have to watch out sometimes if it'll come at you in a backwards form, and it doesn't really make any difference. Here, the highest power is x squared. And so the same rule applies, and you need to take the coefficient. There's that invisible 1 right there, so that coefficient is negative 1 over 2. And again, it doesn't matter if you're going to infinity or to negative infinity. If the numerator and the denominator have the same degree, same highest power, then it's just going to be the ratio of that. They call it the leading coefficient if you're writing it in descending order. So this is just written backwards, but it's still the same thing. Okay? If the degree of the numerator is bigger than the degree of the denominator, then you have what's called unbounded behavior. So this is going to go off either positive infinity or negative infinity. Technically, this answer does not exist. Right here. Doesn't matter, positive infinity or negative infinity. The answer is does not exist. However, you can give a little more information if you note whether this graph is increasing without bound or decreasing without bound. So ask yourself what's going to happen if you plug in large positive numbers compared to plugging in large negative numbers. And there's two different ways you can do that. You can think of try to think of just the sign of your numerator and the sign of your denominator. I think this works most of the time. Every once in a while I run into a little trouble with it. But in example 5, I'm plugging in a large positive number. I'm squaring it. It will still be positive. Multiplying it times 3 and subtracting 2, it will still be positive. In the denominator, I'm plugging in a large positive number, multiplying it by 4, still positive, adding 1, still positive, positive over positive, tells us that this limit, while it does not exist as a technical answer, sometimes we will say it equals infinity, which means increases to the right. As x approaches infinity, y also approaches infinity. It's increasing without bound to the right. Okay? If you take that same function, number 6, and you plug in negative numbers, negative 1 million, negative 2 million, the numerator, again, by the time you square it here, is going to stay positive. But in the denominator, you plug in negative 1 million, you're going to have a negative denominator. So in this instance, it would be, doesn't actually equal negative infinity, but it's headed towards negative infinity. It decreases to the left. Okay? And again, the technical answer is the limit does not exist, but sometimes the knowledge of whether it's increasing or decreasing can be helpful to putting all the pieces together. Okay? And the next situation, example 7, the degree of the denominator is larger than the degree of the numerator. That means the denominator is getting big at a greater rate than the numerator is, and your horizontal asymptote, or your limit rather, is going to be 0. It's sometimes interesting to figure out whether the graph is going to come down at the asymptote or up at the asymptote, and we'll deal with that a little bit later on. Okay? But it's still, again, just figuring out positives and negatives usually. Okay, the next one, I'll put this one in the wrong place. Oh well, the numerator, a higher degree than the denominator. So this one is going to be does not exist. Should put this one before does not exist. And again, just stopping to figure out whether this value is going to head off to positive infinity or negative infinity. I'm going to show you the other way. You can do that thing I showed you earlier about just thinking through plugging in massive values. But you can also do the analytical technique I said of dividing by the power. So I'm going to divide everything by x, and I would get 2 over x, and a plain x here, and in the denominator I would get 1 minus 1 over x, and think through this structure. Sometimes it's a little easier to see whether you're going to go to positive or negative. This goes off to 0, and you can see I'm plugging in a negative, there's a minus here, and I'm plugging in, quote, negative infinity. In the denominator, this goes off to 0 and I'm over 1, so this whole thing turns out to be positive. Again, the actual answers does not exist, but if you look down and you see the choices have negative infinity or positive infinity, you would say that this one is approaching positive infinity. All right, number 9 is not technically a rational function because those exponents are fractions, but the rule still applies. The degree, if you will, of this is 3/2 and 3/2. It's the same, so we can apply that same rule, even though it's not technically a rational function. It still works. And on number 10, sometimes, you know, they like to throw little tiny twists at you. I give you f of x. Here's f of x, this polynomial, degree 3. And then I ask you about some other function, which is defined by f of x divided by x cubed. So you could stop and write the whole thing out if it helps you. Or you could have just noticed that they both have degree 3, and that means the limit is going to be the ratio of the coefficients here and here, 2 over 1, or the limit is equal to 2. All right? Okay, so make good use of that shortcut. It can save you tons of time. I can't think of any time where I require you to show that analytical method, although it is a method you want to just sort of hang on to. Might be helpful sometimes. All right, there is a specific circumstance you're going to see in this class where we get 2 different horizontal asymptotes. And it tends to occur when your numerator is a polynomial, actually usually linear, degree 1, which is linear. And your denominator is not a polynomial, but it's got the square root and it's got x squared. So you can see how you could think of that as being degree 1 as well. And I'm going to work through the analytical process for this. You can see the steps. If you happen to pick up on a shortcut and you can always get this right, that's great, but I want you to see the analytical process for this as well. So the first thing I need to point out is that if you are looking at x, at a positive x value, and I ask you what's the square root of x squared, then the answer is x. So for example, if x is 4, the square root of 4 squared is 4, okay? If you are looking at a negative x value, and I ask you what's the square root of x squared, the answer is not x, because the answer to a square root has to be a non-negative number. So, for example, if x is negative 4, and I say, what's the square root of negative 4 squared? That's the square root of 16, which turns out to be positive 4. X was negative 4, but the square root of x squared is positive 4. So our statement here is that if x is negative, then the square root of x squared is not x, but it's the opposite of x, so that we end up with a non-negative number. Stop and make sure you understand that. Okay? And one other little thing is to recognize that I can write, well, I'll get to that in a few minutes. Okay, sorry. So let's work through the analytical process of finding this limit. All right, and you will remember from the beginning of the notes that I said we were going to divide by the highest power in the denominator. And I know there's an x squared here, but it's really a square root of x squared. So we're going to divide by just plain x, right? So I think I'm going to take this down. I do have to write another limit statement, but I'm going to come down underneath it because this is a little bit messy. I'm going to do 3x divided by x minus 2 divided by x, and the square root of 2x squared plus 1 all divided by x. So my numerator becomes 3 minus 2 over x. And here's the thing in the denominator that you need to see. As long as x is positive, then I can say that x is equal to the square root of x squared. So this right here, this x right here, I'm going to change it into this. When you do it once or twice, the steps go a lot faster. So my numerator has cleaned up nicely. And if you look at this denominator as one giant square root, notice that this is an x squared because it's the square root of that. Then my denominator becomes the square root of 2 plus 1 over x squared. That's where I'm headed to. I go back and write my second limit statement using this. 3 minus 2 over x, the square root of 2 plus 1 over x squared. And note what goes off to 0. This goes off to 0. This goes off to 0. And my answer turns out to be 3 over the square root of 2. It's a positive answer. 3 over the square root of 2. I'm going to take that same problem, but I'm going to take the limit as x approaches negative infinity. And again, I'm going to have to write a second limit statement here. I'm going to do the exact same process. I'm going to take 3x divided by x, 2 divided by x, square root of 2x squared plus 1, and divided by x. And then here's where the difference comes in. The numerator is not different, but right here, because we are looking at x approaching negative infinity here, that means my x value must be negative. And so therefore, x does not equal the square root of x squared. That's not what it equals. I think what I said earlier was the square root of x squared equals negative x. And I'm just going to rewrite that, pop that negative over to this side, and say that x is the negative square root of x squared. Again, I'm looking at x's that are negative, so I have to get a negative value. So right here, I will have the square root of 2x squared plus 1 over negative the square root of x squared. And it just introduces this negative in right there, right like that. Okay? So the rest of it, just like the other one was, except now there's a negative on the outside of our square root. So it looks just like the other one, but you have that negative on the outside, okay? So you're going to take that rewritten function, this, make it your second limit statement. And this goes to 0, this goes to 0. So I get an answer of 3 over negative square root of 2, or negative 3 over the square root of 2. If you were to take a look at this graph in your calculator, you would see that to the right, I don't have a picture of the whole graph in front of me, but to the right, this is 3 over the square root of 2. The graph is coming up here. I think it looks like this. I'm not 100% certain. And to the left, it's going to negative 3 over the square root of 2. So this is an example of a double passage. Okay? All right. The next thing is to look at the function e to the x, and how are we going to do limits at infinity when e to the x is there. You can't use that same rule because it doesn't have the degree like you do in those when the exponents are different for everything. However, you should know, without thinking about it too much, that the limit as x approaches infinity is infinity. It increases without bound. And the limit as x approaches negative infinity is 0. And we're going to use these two pieces of information to help us think through functions that contain e. So here's my function. And what I want to know is what's happening as x approaches infinity for this function. And also what's happening as x approaches negative infinity. So we'll do it one at a time. Okay? All right, so we've got here this little creature, e to the negative x, which is the same thing as 1 over e to the x. And the graph of that, instead of the graph of, it's that flipped picture here, 1 over e to the x. So this function, as x approaches infinity, the y approaches 0. And as x approaches negative infinity, the y approaches positive infinity. So this little piece right here, this, as x approaches infinity, this piece approaches 0. We get number 1, which is 1. So you just want to try to pull out little pieces of it and see if you can figure out how to get something to approach 0 and get out of the problem. Sometimes you do have to rewrite things a little bit for that. What would happen if I had x approaching negative infinity for the same thing? Okay? What would happen is I have x approaching negative infinity. All right, well, what's happening to this when x approaches negative infinity? It's heading not towards 0, but it's heading towards positive infinity. This is the graph of it. E to the negative x is this graph right here. And right over here, it's approaching negative, it's approaching positive infinity. It's rising over there. So you're going to be thinking in your head, you're thinking, I have 1 over 1 minus a great big giant huge number. And 1 divided by a great big giant huge number is a little bitty tiny number, and that one's going to go off to 0. So I've only really given you sort of one example, kind of two circumstances, but when you get an e to the x or an e to the negative x and you're asked to deal with limits, take it back to these graphs, these basic function, e to the x, and think about the limit at negative infinity, at positive infinity, and think about your basic transformation. So this is the graph of e to the negative x right here, e to the negative x, which is the same thing as 1 over e to the x, and your other basic transformations might be able to help you as well. Okay, the next one is a trig one. Back way, long time ago, we learned these two limits, and we memorized them. The limit as x approaches 0, here, sine x over x is 1. This is an oscillating behavior. And then we said also the limit as x approaches 0 of x over sine x, that's also 1. There were two other ones that involved cosine, and I'm not going to bring those back to our minds right now. There's a second one that we need to learn, and that's the limit as x approaches infinity, okay? This is that graph I showed you in class today. I thought it was a trig one, it is. You take sine x, which basically bounces between 1 and negative 1, but divided by an increasingly larger number. Essentially, it's just going to get shorter and shorter and shorter until it never actually arrives here, but it gets very, very, very close to 0, okay? The key to this, and using it in multiple ways, is that that argument, that denominator, and that value right there all be the same thing, okay? All be exactly the same thing. So if you had the limit as x approaches infinity of the sine of 2x, and it's over 2x, well, you could say, well, if x approaches infinity, then 2x approaches infinity, and now all of these are the same thing, and that answer will still be 0. This is one you need to memorize, one of the limits that needs to go into your memory, okay? And again, without discussion here, we'll do the limit as x approaches infinity of cosine of x over x, that's also going to be 0. And so is the limit as x approaches infinity of tangent of x over x. That's also going to be 0. Okay, so add those into your memory compartment. And then hopefully that'll help you get some of the trig ones in the homework stuff. All right, last thing. You did this last year, slant or oblique asymptotes. These occur in one specific circumstance that we're dealing with. And that's when you have this rational structure. And they occur specifically with the degree of the numerator is equal to the degree of the denominator plus 1. So this is when you get a line as a slant asymptote. You never get a slant asymptote when you have a horizontal asymptote. That doesn't happen. If you think about how to find that horizontal asymptote in this case, you would see that it doesn't have one. But this is a case where the numerator is exactly one higher than the denominator. Right? So the degree of the numerator is 2, the degree of the denominator is 1. That tells me that there's going to be a linear but slanted asymptote. Not horizontal, but slanted like a straight line. So the way that you find it is by doing long division. You can also do synthetic division, although I'm not going to remind you how to do that. I'm going to remind you of long division. Just divide. If they factor, that would be nice, but it's not, most of these don't factor. So just make this division, and I think you'll probably remember how to do this. X times x is x squared. X times minus 2 is minus 2x. And then you subtract 2x minus, change colors, 2x minus negative 2x is 4x. Bring down the 4. Hopefully this is ringing some bells. And this is going to be a 4. 4 times x is 4x. 4 times minus 2 is minus 8. And you subtract. Watch your subtraction again. These two have to go away when you're doing long division. If you don't make those two go away, you've done it wrong. And then plus 4 minus negative 8 is plus 12. So you take your function here, your original function, and you write it as this line, x plus 4. That's going to be a line. And then you write your remainder, this, over your denominator. That's rewriting the functions. These two functions are the same thing. You worked with it in the top form mostly, but if you typed both these functions in your calculator, they are identical. There is no difference. This bottom form here tells us what the slant asymptote is, because the slant asymptote will be this line. And what it's basically saying is that slant asymptote or oblique asymptote, it's basically saying, okay, by the time you get really, really, really big numbers, this little piece right here has practically no effect on the shape of the graph. For all practical purposes, it's not doing anything, because you're plugging in 12 divided by, I don't know, 7 million, which is negligible in almost all circumstances. So this is called the slant asymptote, and that means at the end of the graph, whatever this graph looks like, and I'm going to go back and just remind you that it did have a vertical asymptote right there at x equals 2. A vertical asymptote, and then it's going to have a slant asymptote, and this equation is y equals x plus 4. And I think that you'll kind of remember that these graphs were either, I'm not going to work this all the way through, but you either had this piece here, or you had this piece here. There was one of those, but not both. And on the other side of the vertical asymptote, you either had this piece here, or this piece here. And there could be any combination. So I'm doing it in red. It could be this one and this one. That's possible. Or I'm going to do this in blue. It could be this one and this one. That's possible. So there's any kind of combination. One less possible. There's 2 or 3 other ones. You could have this one. Oh, that did green. Sorry, you could do this one. And either that one or the other one down here at the bottom. One or the other. That's what those slant asymptote graphs look like. So let me do one more example for you. Degree of the numerator is 2. The degree of the denominator is 1. If I said to rewrite it, or to find the slant asymptote, you need to do long division. 2x squared. It's a good idea to put placeholders in all the way down to the constant, 2x squared plus 0x plus 0. And you're saying x times what is 2x squared? That gives you 2x. 2x times x is 2x squared. These two have to be the same. The first term has to be the same, and the second term is whatever develops. 2x times negative 3 is negative 6x. Remember that you are subtracting, not adding. 0 minus -6 is 6x, and bring down the 0. The next thing you're saying is x times what is 6x, so you need a plus 6. 6 times x is 6x. 6 times -3 is 18. You are subtracting, and you get a remainder of 18. If I ask you to rewrite the function, the rewritten function is this. These two functions are the same. There is no difference. Just like when you factor, they're the same function. Absolutely no difference. If I ask you, what's the slant or oblique? The other word is oblique. The slant or oblique asymptote is this part. Y equals 2x plus 6. And you would draw that asymptote in. Okay? That's it. Hopefully you won't have any trouble at all with your homework.